Modern medical imaging generates staggering amounts of data, but the physical limitations of the hardware inevitably introduce noise into the final readouts. In environments with very low light or low radiation counts, we run into extreme Poisson noise. The true signal gets buried under violent random static. To solve this mathematically, we look at a highly controlled dataset, a 256 by 256 pixel phantom image, specifically constructed to mimic the porous structure of cancerous bone. This shows panel A from our dataset, representing the raw gamma camera readout. The target is unintelligible. Compare that to panel C on the right, the restored posterior mean image. The underlying structure is exactly separated from the noise. Our objective is to execute that exact mathematical recovery without causing a computational meltdown in the process. Traditional continuous spatial models handle data by calculating the absolute distance between every single point in the space. For a 256 by 256 image, you track 65,536 pixels. Building a standard covariance matrix requires computing the strict relationship for every possible pair. That takes O of n cubed time. The dense matrix calculations quickly stall out. To bypass this, we move away from continuous models and instead analyze discrete spatial variation using Gaussian Markov random fields. A Gaussian Markov random field entirely discards the concept of a dense global covariance matrix. It relies on local conditional independence to build a sparse precision matrix. By restricting our math strictly to immediate neighbors, we strip out the dead weight of tracking distant points. To understand how those localized neighbors operate, we must look at the statistical graph theory behind conditional independence. This diagram displays a standard 4-node conditional independence graph. Look at the missing links. Because there are no edges connecting nodes 1 to 3 or 2 to 4, those pairs are conditionally independent. This is the pairwise Markov property. The presence or deliberate absence of these individual edges entirely dictates the dependency structure of the system. A Gaussian Markov random field is defined strictly as a random vector that maps exactly to the structure of one of these undirected graphs. When we remove edges, we intentionally eliminate variables from the equation, collapsing the computational weight of the network. That graph structure translates directly into a statistical precision matrix, which we label as Q. If we map a 4-node graph into a 4x4 matrix, the conditionally independent pairs Q13, 31, 24, and 42 populate as exact zeros. According to Theorem 12.1, the joint distribution is parameterized by a symmetric positive definite precision matrix. The zero entries dictate the conditional independence. Slight pause for effect. When we apply this to the 65,000 pixels in our gamma ray image, the matrix becomes incredibly sparse. It is almost entirely zeros, with active data restricted to a tight band along the diagonal. A traditional covariance matrix would be packed with data in nearly every cell. Our precision matrix is mostly empty space. That extreme sparsity is the exact mechanical advantage that allows us to solve massive spatial datasets. Let's apply that matrix math to the restored image in panel C. In this conditional specification, the expected value of a single localized pixel is determined solely by the weighted inputs of its immediate north, south, east, and west neighbors. Basing an entire image on local pixel-to-pixel conditionals creates a mathematical tension. We need to guarantee that these local rules sum up to a mathematically proper global joint probability distribution. Brooks' lemma provides the proof. It demonstrates that as long as the local conditionals are valid, they map uniquely to a consistent global joint density. The only strict requirement is a symmetry constraint, where Qij strictly equals Qji, ensuring the precision matrix remains symmetric positive definite. Brooks' lemma guarantees that we can assemble highly accurate global models using nothing but localized rules. With the spatial model clearly defined, we can move on to computational inference. A standard approach relies on a single-site Gibbs sampler, which moves through the image and iteratively updates one pixel at a time based on its neighbors in O of n operations. While functional, MCMC methods come with significant computational costs. including long burn-in times, persistent Monte Carlo error, and constant need to verify convergence. Because our precision matrix is sparse, we can bypass MCMC entirely using exact numerical algorithms, specifically the Cholesky factorization, which splits the Q matrix into a lower triangular matrix L and its transpose. By solving LV equals B through forward and backward substitution, we calculate exact marginal variances in O of n to the 3/2 time. The linear algebra allows us to skip Monte Carlo approximations altogether, yielding immediate, deterministic answers. We can extend this architecture beyond two-dimensional grids and map sequential, three-dimensional data. This series shows biological cells from confocal microscopy across 5 vertical frames. Notice the specific spatial coordinate highlighted across all 5. In a multivariate Gaussian Markov random field, a spatial node is a continuous p-vector tracking downward through the layers, rather than a flat scalar. The conditional neighborhood expands. A pixel is now conditioned on its flat 2D neighbors in the current frame, plus its exact coordinates on the z-axis in the frames directly above and below it. The precision matrix absorbs this multidimensional complexity by using block elements, denoted as Q tilde ij, instead of standard single numbers. Adding temporal or depth dimensions simply modifies the block structure of the matrix. The crucial sparsity of the system remains intact, allowing it to scale effectively. We began with random noise completely burying a geometric target and achieved clean data recovery by strictly limiting how we calculate spatial relationships. By prioritizing local conditional independence over global covariance, we strip away redundant calculations. Graph theory maps our missing edges into exact zeros, creating a sparse precision matrix that circumvents the bottlenecks of continuous models. Cholesky factorization takes that sparse matrix and rapidly executes exact inference without the slow burn-in of iterative sampling. Gaussian Markov random fields map localized rules into mathematically pristine global distributions, allowing us to accurately process the most massive spatial datasets.